Okay, so we will talk about Rabin Cryptosystem. So, we have seen the Chinese remainder theorem, and it also use what is called quadratic residue. So, let us just recap what is a quadratic residue. What do we mean by quadratic residue? Mod some prime modulo p. So, this we know that where p is a prime, typically odd prime, and a is an integer, then the definition is a is called a quadratic residue, mod p if and only if these modular equations y square equal to a mod p has a solution in ZP. So, that means if there exists a y in ZP such that y square is congruent to a mod p. So, that means a should have a square root. So, basically we can write y is basically the root over of a, something like that. I mean here root over means this sense, quadratic residue. Okay, so, this is the definition of quadratic residue. We have seen this, and now, so let us take an example. Suppose p is equal to 11, then what are the integer with the quadratic residue mod 11. So, suppose we are talking about z 11. So, p is 11. So, then so y must belongs to z p. So, we will take the possible y. So, let us take plus minus 1 square is 1, plus minus 2 square is 4, 3 square is 9, plus minus 4 square is basically 16, but it is under mod 11. So, it is basically 5, then plus minus 5 square is basically 3, plus minus 6 square is 36, then mod 11 it will give us 3 again, and then plus minus 7 square. So, these are possible y's basically is 5, plus minus 8 square is basically 9, and plus minus 9 square is basically 4, plus minus 10 square is basically 1. So, basically, so these are our possible y. So, these are the number which are having, this is our a, I mean this is having square root. For 4, this there are 2 square root, plus 2 minus 2. So, plus 2 is basically 2 and minus 2 is basically this 9. So, this way. So, these are the number. So, 1, 3, 4, 5 and 9 are basically quadratic residue modulo mod 11. Quadratic residue mod 11. So, under Z 11 these are having the square root. Okay. So, now in general how we can check whether A is a quadratic residue or not. So, we have seen this is by Euler criteria. So, we have given a prime number p and we have given a and how to check A is a quadratic residue or not. So, this is by the Euler. So, Euler criteria to check the quadratic residue. So, p again the same thing, p is a prime, let p be a prime and a is an integer and we know this theorem that A is a quadratic residue, mod P if and only if a to the power p minus 1 by 2 is congruent to 1 mod P. So, this theorem is by Euler's, and we have seen the proof in our mathematical background portion. So, this is by Euler. So, this is to check if this condition satisfy. If this is satisfy, then A is a quadratic residue. So, this will tell us whether A is a quadratic residue or not, but this will not give us the square root. So, to get the square root, so this will only tell us whether A is quadratic residue or not, yes or no. Now, if it is no, there is no question go further, but if it is yes, then how to get those, how to get the y such that y square is congruent to x mod p. So, how to get the square root of x basically. So, how to get those solutions y. So, that is the another questions that we require for our Rabin cryptosystem. So, in general it is hard, but if p is of the form 3 mod 4. Okay. So, p is an integer, p we are choosing as a prime, p is an integer basically. So, so any integer can be written as, if this is mod 4, any integer can be written as either 4k, 4k plus 1, 4k plus 2, 4k plus 3. So, any integer will be either of this form, either it is 4k form, k is another integer, or 4k plus 1 form, or 4k plus 2, or 4k plus 3. Okay. Now, p is a prime. So, these two are odd numbers. So, this is not prime. So, this is automatically cancelled. So, we have to choose p as a prime. So, this 4k and 4k plus 2 we cannot choose. So, we have only two options, these two. So, this means p is congruent to 1 mod 4, and this means p is congruent to 3 mod 4. So, we will basically consider this for our Rabin cryptosystem. Why? Because for this the square root, getting square root is easy. There is a deterministic polynomial time deterministic algorithm to find the square root. Suppose we have an equation like this, y square equal to x mod p. Okay. Now, we have to find square root of x. I mean, suppose x is a quadratic residue. So, we have to find the solution y. So, that if p is of this form, okay, then we know the solution. Then the solution will be of the form of this is basically solution will be like this, p to the power. So, this is basically y. So, suppose anyway this is suppose okay, let it be a. So, if it is a, then we know that solution is basically plus minus a to the power p plus 1 by 4. Let me write very carefully, plus minus a to the power p plus 1 by 4. Why? This with these two are the mod p. So, this is the solution for this when p is equal to of this form. Why this is a solution? Because if you take the square of it, provided A is a quadratic residue, that means provided that Euler criteria satisfy. So, if you take the square of it, so this is basically y we are suspecting. If you take the square of this, So, this will give us what? This will give us, this is y to the power. So, p plus 1 by 2, sorry, 1 by 2 mod p. Now, this is basically sorry, a to the power. This is basically a to the power p minus 1 by 2 into a mod p. Now, this by Euler criteria, this is basically 1. So, this will give us a mod p. So, this a mod p. So, that means this 2 is the solution for this system of this modular equation, provided p is of this form. Now, if p is not of this form, if p is of this form, then there is no polynomial time deterministic algorithm to solve this, but there is a algorithm which is polynomial time, but non deterministic, that is Las Vegas algorithm when p is, but that is not non deterministic, p is 1 mod 4. Okay, but for getting solution in a polynomial time deterministic way, we need to assume this. So, this is the assumption we will make for our Rabin cryptosystem in order to get the square root of this a. So, we will come to Rabin cryptosystem. So, this is a public key cryptosystem, and this is invented before RSA, but this cryptosystem is having ambiguity. This hypertext is ambiguous. So, this is a public key cryptosystem. So, Rabin cryptosystem. So, it is a public key cryptosystem, and it was invented much before RSA, but this is having some drawback, we will come to that. So, since this is a public key cryptosystem, so we have to get the public key private key pair for the receiver. Now, suppose Alice wants to send a message to Bob, okay, in a public key setup. So, that means Alice need to get Bob public key. Sorry, this is Alice need to get Bob public key, and Alice will encrypt this using the Bob public key, encrypt the message. Alice will choose a message, and Alice will encrypt the message using Bob public key, and Bob is having Bob. This is the encryption, public key encryption, and Bob is having Bob secret key. So, what Bob will do? Bob will decrypt y using Bob secret key, and this is basically db of e b of m. So, this should give us m back. So, this is decryption, this is encryption, this is the public key setup. Now, the question is, so Bob is the receiver. So, Bob has to generate this public key private key pair, and then Bob has to announce this is my public key. Then only Alice can send a message to Bob. So, this is this public key private key pair setup. This is the key generation algorithm, key generation. So, this key has to generate by the Bob. So, this is the setup phase which has to done by the Bob, because Bob is the receiver, Alice is sending message to Bob. Okay. So, so at the setup phase, what Bob will do? So, Bob will choose 2 prime P and Q, 2 primes such that both are congruent to 3 mod 4. This is we have seen in order to have the square root. I mean, we will come to that where we need this to get the solution for the quadratic residue. So, the square root. So, this is the condition, and this is one of the restrictions for Rabin cryptosystem. But if we choose congruent, because these are prime, so if we choose congruent to 1 mod 4, then we have to apply the Las Vegas algorithm, which is not deterministic. Anyway, so this is the setup. So, choose this and then Bob compute P into Q, and this is the key of Bob. So, this N P Q. So, this is the key space of Bob, and this is the public key of Bob E B, which is basically N. This is the public key of Bob, and these two is D B, which is the secret key of Bob or the private key. This is the public key of Bob, and this is the private key or the secret key of Bob, P and Q both. So, Bob keep P Q to himself, and Bob make this N public. So, Alice will be knowing this N, Bob public key. Okay. Now, the plain text hypertext space is basically Z n star. Okay. So, Alice will choose a plain text from Z n star. Suppose X is the plain text. So, Alice is choosing a plain text from Z n star, and Alice is having Bob public key. So, what is the encryption? Encryption is basically EK of, so EK of, this is the Bob public key, the key, X is basically X square mod n. Okay. So, Alice will just do the square root of it and then take the mod, and this is the Y, this is the ciphertext. Okay. And this ciphertext Alice will send to Bob Y. Okay. Now, this is Alice can just make the square root, square it and take the mod n and send it to Bob. So, this is the encryption. This is Rabin encryption. Okay. So, now Bob, how Bob will decrypt it? So, Bob has to get back X, Bob is getting Y. So, the first of all, so that is why it is, so there could be many X which is mapping to Y. So, that is why this is not a injective function, this is not a injective function, that is one of the drawback of this crypto system. So, Bob will be getting many X for which the Y is the ciphertext. So, Bob will be confused which X is the plain text was chosen by the Alice. So, now what is the decryption, how Bob will decrypt it? So, Bob is having PQ is the Bob public key. So, now this is basically we have, so Bob is getting Y. So, Y is basically what? Y is basically some X square mod n. Now, Bob need to get back X. So, now how Bob will get back X? So, that means X square equal to Y mod n. Now, by Chinese remainder theorem, so this can be breaking into two parts. So, X square is equal to Y mod P and X square is congruent to Y mod Q. So, these two system, if this two system has a solution, and that solution is basically this X square equal to, so this is just a Z mod n. So, this is coming from Chinese remainder theorem. Now, the question is how to solve this. Now, we know that, so for this is equation 1, this is equation 2. So, let us deal with, so this is the decryption process Bob is doing. Let us deal with equation 1. So, from equation 1, X square is congruent to Y mod P. Now, here we assume P is 3 mod 4 in order to get the solution for these equations. So, then what is the solution? We know the solution is basically plus minus y to the power p plus 1 by 4 mod p. Okay. So, we have two solutions from here. For this is the solution for this, and from equation 2 also we have two solutions, plus minus y to the power q plus 1 by 4 mod q. So, basically we have 4 solutions, and these are the possible plain text, and from here. So, that is why it is the hypertext is not it ambiguous, it is not unambiguous, it is ambiguous, because we have 4 x which is mapping to that y, the hypertext. So, the Bob will be confused among these 4 which one is Alice was chosen. So, that is why this cryptosystem is having the ambiguity. So, which one is Alice has chosen. So, let us take an example. So, basically these 4, so plus this minus this mod p plus this minus this mod q. So, these 4 are the possible plain text. Now, Bob has to think which one is the plain text Alice was chosen. So, let us take an example of this cryptosystem. So, okay, so example of Rabin cryptosystem. Example of Rabin cryptosystem. So, so now Alice wants to send a message to Bob. So, Bob has to generate this key generation phase or this setup phase. Bob has, this is the key generation phase. This has to be done by Bob, because Bob is the receiver. So, if I want to send a message to Bob in a public key setup, I need to get Bob's public key. So, this key generation has been done by Bob. So, once Bob complete this key generation, so then Bob will be having Bob public key private key pair excuse me, then Bob will make Bob's public key as public in a public domain or can announce anyway. So, the setup phase we know we have to choose 2 prime, but they must be congruent to 3 mod 4. So, let us take 2 prime, p is equal to say 7 and q is equal to say 11, and Bob compute this Bob's public key, which is basically p into q, which is 77. So, this is basically EB of Bob public key, and this Bob make public. So, EB of Bob is basically 77. Okay, so this is the setup phase and it is done. Now, so the key space and the hypertext space is basically J star 77. J star 77 means it is the all integer less than 77 which are relatively prime to 77, and the cardinality of this number is 577. So, this is basically cardinality of this number is 577. And this is basically 5 this is 5 pq. So, this is basically p minus 1 into q minus 1, and this is how many elements are there? This is 6 and this is 10. So, 60 elements are there in the plain text space. Okay, and all the elements basically Zn star are, this is basically set all the elements, all the integer, all the positive integer less than 77 which are relatively prime to 77. So, this is the star. So, all the elements which are less than 77, but it must be relatively prime too. So, Alice has to choose a plain text from this, or the message has to be coming from Z77. Suppose message is X, Alice is choosing a message which is, and then what is the encryption? Encryption is basically EK is basically, so K is this, EK of X is basically x square mod 77, and this is the Y, and Y is the ciphertext Alice is sending to Bob. So, what Bob will do? Bob has to decrypt it. So, decryption using the secret key of Bob. So, this is basically square root of this. So, square root means we have to perform those solution for this quadratic residue equations. Okay, so let us take an example. Suppose Y is 23. So, Alice choose a message X, and for which this is coming to be 23. Now, 23 is the ciphertext. So, 23 is going to Bob. So, how Bob will decrypt it? So, that is the, and there will be some ambiguity will be there. So, to decrypt it, so Bob has to get the solution. So, by Chinese remainder theorem, so Bob has to find x such that x square is congruent to, actually x square is congruent to 27, 23 mod 77, but this from here we can say this is by Chinese remainder theorem, x square is congruent to 23 mod 7, this is one equation, and x square is congruent to 23 mod 11. So, we have to solve these two separately, and then the solution will give us the solution for this. So, if we take this equation, if this is equation 1, equation 2, we do not have 1, 2 here. So, this is basically from equation 1, we can say that 23 to the power p plus 1 by 4 plus minus. Okay. So, this will give us mod 7. So, this and plus minus 23 to the power 11 plus 1 by 4 mod 11. So, these two will give us the solution plus minus 10 and plus minus 32 mod 77. Okay. So, basically x is basically possible x is basically 10, 32, then minus 10 which is basically 67, and minus 32 which is basically 45 and 67. So, these are the possible plain text corresponding to this ciphertext 23. These are possible plain text. Bob is getting possible plain text corresponding to the ciphertext corresponding to the ciphertext 23. So, Bob is getting all this plain text. Now, Bob will be confused which one is the correct plain text. So, that is why this system is not unambiguous, this is ambiguous system. So, Bob has no way to know what is the plain text used by the Alice among these. So, Bob is getting 4 plain texts from this ciphertext 23. So, Bob will be confused. So, now Bob has to somehow guess, okay, which one could be the plain text. If it is the age of Alice, then maybe 10 is not possible, 67 is not possible, 45 may be not possible. So, maybe 32. So, some type of guess is required. So, that is why this crypto system became not popular because of this ambiguity. Okay, thank you.